till now we have seen how to solve or how to analyze the single line to ground fault in a power system. In that we have already considered the effect of fault impedance. Now we will see how to analyze double line to ground and double line to line fault in a power system. We are going to assume that initially the power system is a balanced system, except at the point of fault. When the fault occurs, then it is the only unbalance which is in the system. So we are going to assume everything else balance in the power system. So let us see the case of line to line fault in the power system. Let us say this is phase A of the power system, this is phase B of the power system, this is phase C of the power system. It is having some current, let us say IA, IB and IC. Okay, IA dash, IB dash and IC dash. Now let us say at this point P, the line to line fault has occurred in the power system. We are assuming that there is an impedance which is involved in the fault, and this impedance is, let us say, ZF, and at this point the voltage of phase A with respect to ground is VA, this is VB with respect to ground, and this is VC with respect to ground. Okay, now initially we are also assuming that the pre-fault voltage is with respect to neutral is VF. Okay, now let us say this is current IB which is flowing into the fault, and this is current IC which is flowing into the fault. Okay, now from KCL we can easily see that IB plus IC, if I use KCL let us say at this point, IB plus IC is equal to 0, or IB is equal to minus of IC. Now from KVL we can also see that VB minus VC is equal to IB into ZF, the fault impedance. Okay, so let us say this is equation number 1, this is equation number 2. Okay, now we want to find various sequence components. So what we will try to do, we will try to find the values of various sequence currents and voltages using these two equations. Okay, because these two equations are going to signify a line to line fault in the power system, and there is the fault impedance also. Okay, so what we will do, we will try to convert this VB and VC into their sequence components. So VB can be written as VB1 plus VB2 plus VB0, or A square VA1, A VA2 and VA0. Similarly, VC can be written as VC1 plus VC2 plus VC0, or if I want to write VB minus VC, what I can write, this is VB and here I will write VC. VC1 is nothing but A times VA1, VC2 is A square VA2 and this is VA0, and it is equal to IB ZF. Okay, now this is VC. So here from this equation we can see that A square minus A into VA1, that is this A square and this A for VA1, plus, or if I want to take A square minus A as common, so I will write it as minus A square minus A VA2, and this VA0 and this VA0 will get cancelled out, equal to IB ZF. Now we also know that IA0 is equal to IA plus IB plus IC divided by 3. Now this IA into the fault is equal to 0 because it is now open here. So IA0 is equal to IB plus IC over 3, or IB plus IC is equal to 3 times IA0, and we also know that IB is equal to minus IC, or IA0 is equal to 0. So we know now that IA0 is equal to 0. Okay. Now we know that A square minus A, let us derive this. Let us this reference. So A square will come here. This is 240 and this is angle 120, and A will come here. This angle is 120. So this is A square and this is A. A square minus A will be so this value is A square minus A. Now from this diagram we can clearly see that this is minus J, and if it is 1, this is angle 60 degree, then it will be root 3. So A square minus A is nothing but minus J root 3. Okay, so I will put this value here, minus J root 3 VA1 minus of J root 3 VA2 is equal to IB ZF. Okay, so I can clearly see that I can write it as minus J root 3 VA1 plus J root 3 VA2 is equal to IB ZF. Okay, let us say this is equation 3 and this is equation 4. Okay, now up to this point we have got some equations, but still we are not able to see any relation between various sequence components. So we will further manipulate them. We will also try to find the value of IA1 and IA2, and we will also try to see the relation between VA1 and VA2. Now we already know that IA0 is equal to 0. So there is no zero sequence current in the zero sequence network. Okay. Now we need to find the relation between IA1, IA2, VA1 and VA2. That we will see in the next slide. Now let us further manipulate these 4 equations. Now we know that IA is equal to 0 and IB is equal to minus IC. So first we will try to write the equation for IA1. It is nothing but 1 by 3 IA plus AIB plus A square IC. Okay, so it is 1 by 3 this is equal to 0, and IB is equal to minus of IC. So AIB minus A square IB. So it is 1 by 3 A minus A squared IB. Now A minus A square is nothing but J root 3. So IA1 is equal to J by root 3 IB. Okay. Now let us say what is the value of IA2. It is 1 by 3 IA plus A square IB plus AIC, or it is equal to 0 and this is equal to minus IB. So I can write it as minus J root 3 by 3 IB, or minus J by root 3 IB. Let us say this is equation number 5 and this is equation number 6. Now from equation number 5 and 6 we can see that IA1 is equal to minus of IA2. So this is equation number 7. Now something has turned up now, that we have got some relation between IA1 and IA2, and we know that IA0 is equal to 0. So somehow the network will be something like that, that IA1 and IA2 will add to 0. Okay, and IA0 is 0, so the 0 sequence network will be open. So we have got some relation now. Now let us see what is the relation between VA1 and VA2. That we will do in the next slide. Now let us further manipulate the equations. What we will do, we will put the value of VA1 and VA2 in this equation number 4. We know that VA1 is nothing but the pre-fault voltage minus IA1 Z1, and VA2 is nothing but minus IA2 Z2. This is the negative sequence impedance seen from the point P of fault, the Thevenin impedance, and this is the positive sequence Thevenin impedance seen from the point of fault, and this is pre-fault voltage, positive sequence pre-fault voltage. That now these values we will put in the equation number 4. So what we will get, minus J root 3 VF minus IA1 Z1 plus J root 3 minus IA2 Z2 is equal to IB over ZF. Now IA1 is equal to minus of IA2. This is we have seen from equation number 7. So I can write this as just IA1. Okay. Similarly, from this equation number 5, I can see that IB is equal to root 3 over J IA1, or minus J root 3 IA1. That we will put here. So minus J root 3 IA1 ZF minus J root 3 VF minus IA1 Z1 plus J root 3 IA1 Z2. Okay, so J root 3 is common. So we have minus VF plus IA1 Z1 plus IA1 Z2 is equal to minus IA1 ZF. Okay, or IA1 Z1 plus Z2 plus ZF is equal to VF, or VF over Z1 plus Z2 plus ZF is equal to IA1. Now this is one important relation which is again giving us some idea about the interconnection of the positive sequence and the negative sequence network. What does it show? It shows that IA1 is the ratio of the pre-fault voltage and the total fault in the network, the positive sequence impedance, the negative sequence impedance, and the fault impedance. Okay, so these should come in series with respect to this pre-fault voltage. So if I try to form some kind of network in which IA1 and IA2 should join at one place, and this VF Z1, Z2 and ZF should come in series with this network. So somehow we are getting some idea that this type of network should be there. Okay, so the only thing remaining is if we somehow find VA1 minus VA2. Okay, so if we somehow find that VA1 minus VA2 is equal to IA1 ZF, then we will be sure that this is the equivalent connection of the sequence network for line to line fault. Let us try to get this equation also. What we will do? We will use equation number 4 again. Now IB is minus J root 3 IA1 and it is ZF. That I have put in the equation number 4, this value equals to minus J root 3 VA1 plus J root 3 VA2. So minus J root 3 is common. So I will get VA1 minus VA2 is equal to IA1 ZF. Now here we have got this equation which was required. So now we are sure that the various sequence network, positive and the negative sequence network of the power system should be connected in such a way that this is the, let us say, pre-fault voltage VF, this is the reference or the neutral of the system, this is positive sequence Thevenin impedance seen from the fault point, and this is the fault impedance ZF. Let us say this is voltage VA1, this is current IA1, then this will be Z2 and this voltage will be VA2 and this current will be IA2. So for line to line fault, now we can see that the sequence network should be connected like this and the zero sequence network is open. We need not show this in this interconnection. So in this way we can calculate the values of various sequence currents and voltages, and by that we can find the value of various line currents and line voltages and whatever value we will need to find in the power system. Okay, now in the next slide we will try to see double line to ground fault and the various interconnection for such kind of fault. Now let us try to analyze double line to ground fault. Now as the name suggests, in this type of fault what happens? The two phases of the system get faulted to earth also. Okay, now there might be a question in the minds of student that these lines will also be having some impedance, let us say ZL. It is actually true, but practically what we see that usually this kind of fault, let us say this is a tower arm on which the conductors are hanging. Okay, this tower is earth. Now Usually what happens, this insulator gets spark over or there is an arc. Similarly, this insulator might spark over, there is an arc. So what happens, this kind of sparking or arcing will cause double line to the ground fault. Now practically it is seen that the tower footing earth resistance, that is the resistance of this tower with respect to true ground, is comparatively very high as compared to the resistance of this arc. So to reduce the complexity of our analysis, what we assume that this ZL is negligible and we assume that this is a direct short circuit between the phases, and we just assume this impedance in the earth circuit. Okay, so this is the equivalent scenario for double line to ground fault. Now we will try to find the interconnection of various sequence network in such kind of fault. Okay, let me erase this first. Now from this scenario we can see that VB is equal to VC. This voltage is equal to this voltage and this current is IB plus IC is equal to IB plus IC into ZF. Okay, you can clearly see from this network. Okay, now we know that this IA is equal to 0, so IB plus IC is nothing but 3 times of IA0, the zero sequence current. So we can see that VB is equal to VC is equal to 3 times IA0 ZF. Let us say this is equation 1. IA is equal to 0 is one of the equation we have. Okay, and IB plus IC is equal to 3 IA0 is another equation which we have. Now we will try to find various sequence voltages since we want to find their interconnection. Okay, so VA1 is equal to 1 by 3 VA plus AVB plus A square VC. Now VB is equal to VC, so it becomes 1 by 3 VA plus A squared VB. Now we know that 1 plus A square is equal to 0. So A plus A square is nothing but minus 1. So we can see that VA1 is equal to 1 by 3 VA minus VB. Similarly, VA2 will come out to be 1 by 3 VA plus A square VB plus AVC, or 1 by 3 VA minus VB. Now from this equation, let us say this is equation number 2, this is equation number 3. We can clearly see that VA1 is equal to VA2. So now we have got an idea that the positive sequence and the negative sequence network will be connected in parallel. Okay. Now let us see what is the value of VA0. 1 by 3 VA plus twice of VB, because VB is equal to VC, so VB plus VC is equal to twice of VB. Let us say this is equation number 4. Now this equation is not giving us any hint, so let us see, is there any difference between this voltage and this voltage? Is there any relation which is existing between them? So we will try to find VA0 minus VA1. Now it comes out to be 1 by 3 VA plus 2 VB minus VA plus VB. Okay, so it comes out to be, this is got cancelled out, VB. So VA0 minus VA1 is equal to VB, and it is equal to IA0 into 3 times of ZF. So we have got what we have got now, that the positive sequence network and the negative sequence network will be having impedance three ZF between them, so that this is VA1, this is VA0, so that VA0 minus VA1 equals to IA0 into 3ZF. So we have got half picture of the interconnection of the positive sequence and the zero sequence network. Now other half we have already seen that VA1 is equal to VA2. So we will see that VA2 will come in parallel to VA1. So this will be VA2. So now we are getting some picture, some idea that the interconnection of these three sequence network will be somehow in this form. VF Z1, this current is IA1, so this voltage is VA1, this, let us say this is negative sequence impedance, this is current IA2. Okay, so this is again VA2, so VA1 is equal to VA2. Now VA0 minus VA1 is equal to 3 times of ZF into IA0. So this is 3 times of ZF, and this is current IA0, and this is Z0, and this is equal to VA0. So we have got very much good idea that this will be the interconnection of the various sequence network. Now we will try to further solidify this idea by getting some equation of interconnection of these various sequence impedances, that is Z1, Z2 and 3ZF and this Z0, that we will see in the next slide. Now let us further manipulate these equations so that we can have a solid idea how to interconnect these various sequence network. However, we are already having a very good idea of this interconnection, okay, but let us further confirm this. Now we have seen that VA0 minus VA1 is equal to IA0 into 3 times of ZF. We have also seen that VA1 is equal to VA2 and VA0 is equal to 1 by 3 VA plus 2 VB. We know that VA0 can be written as minus IA0 Z0, VA1 can be written as VF minus IA1 Z1, and VA2 can be written as minus of IA2 Z2. Okay, so if I want to write, IA2 is nothing but minus VA2 over Z2, but VA2 is equal to VA1, so it is nothing but minus VA1 over Z2, but VA1 is VF minus IA1 Z1 over Z2. So this is the value of IA2. Okay, now from this we can see that VA0 is equal to VA1 plus IA0 3ZF, or VA0 is equal to VF minus IA1 Z1 plus IA0 3ZF, and VA0 is nothing but minus IA0 Z0. Okay, so we can see that minus of VF minus IA1 Z1 is equal to IA0 is common, Z0 plus 3ZF. So from here we can see that IA0 is equal to minus of Vf minus Ia1 Z1 over Z0 plus 3Zf. So we have got Ia2, Ia0 in terms of Ia1 and Vf. Now we know that Ia is equal to 0. So Ia1 plus Ia2 plus Ia0 is equal to 0, or Ia1 minus Vf minus Ia1 Z1 over Z2. I have put the value of Ia2 from here. Similarly, I will put the value of Ia0 from here. Minus Vf minus Ia1 Z1 Z0 plus 3Zf is equal to 0. Okay. Now on solving, what we will see that Ia1 can be written as Vf divided by Z1, okay, plus Z2 in parallel with Z0 plus 3Zf. On solving this equation, we can find that Ia1 can be written as Vf over Z1 plus Z2 in parallel with Z0 plus 3Zf. Now Z2 in parallel with Z0 plus 3Zf is nothing but Z0 into Z0 plus 3Zf over Z2 plus Z0 plus 3Zf. Okay, now you can clearly see that this Z2 and Z0 plus 3Zf is there in the denominator. So somewhere this is going to give us the same equation. So on solving and manipulating the algebra only, we can easily see that Ia1 is written as the ratio of the pre-fault voltage to the neutral divided by Z1 plus the parallel combination of Z2 and Z0 plus 3Zf. Now clearly this network is again satisfying this equation. We can see that Ia1 can be simply written as Vf divided by this Z1 in series with the parallel combination of these two. So you see that our network is also satisfying this condition of connection of these impedances. So in this way, for double line to ground fault, the sequence network should be connected such that the positive sequence and the negative sequence are like this, such that Va1 is equal to Va2 and Ia1 plus Ia2 is equal to minus of Ia0, and this thing 3Zf is coming between these two networks. Okay, so in this way we can connect these networks, sequence network, and find the value of various sequence component, and from that we can find any value of line voltage or line current by using various normal network equations. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.